Welcome everyone to our demonstration video of EEE 206 Energy Conversion Laboratory course. Here we have come with an idea of a hand crank mechanical to electrical energy storage system. So first of all, in this project we have used a DC generator having 12 volt rated voltage with a speed of 2700 RPM, and it is also a rated speed. Next we have bridge rectifier, and we have used this as a full wave bridge rectifier which will eventually rectify our DC output which has been induced from the DC generator. The third part of our project is a supercapacitor based storage system where we have used 1 farad capacitance, and all of the capacitors have been connected in parallel with each other, giving us 5 farad in total, and the voltage rating of all of them is 5.5 volt. And next, as a load, we have a CPU fan. It's also a DC fan which will work as a load in our project. If we look at the bridge rectifier that we have used here, we have used 1N4007 model diode, and we have installed this bridge rectifier for a particular reason, because during the DC flow in the circuit, if the direction of rotation of this shaft is either on the particular direction or the opposite direction compared to that, then the DC generator will eventually may work as a consuming element instead of supplying power to the entire circuit. Therefore, if we introduce a bridge rectifier in our circuit, it will eventually rectify the DC output, and our DC generator will work as a supplying element whether we rotate the shaft in clockwise position or in anti-clockwise position. Next, we have our supercapacitor based storage panel where we have used supercapacitors having 1 farad capacitance and 5.5 voltage rating. And in this whole storage panel, we have connected the 5 capacitors in parallel with each other to have a total capacitance of 5 farad. And if you look closely in the circuit, we have also used a 7805 IC, which is basically a 5 volt voltage regulator. It has been used for a very particular reason, because the supply that we are getting from this DC generator in our entire circuit can be up to 12 volt, and which can eventually destroy or damage our storage panel, as the voltage rating of these capacitors is only 5.5 volt. To keep safe the whole storage panel, we have used this 5 volt IC, because it will take the 12 volt generator's input and it will convert it to 5 volt and supply it to the whole storage panel. We have also used a simple 1N4007 diode from the IC's output to the capacitor's input, and it has been used to prevent the black flow of charge towards the previous circuit, and after installing it, the flow will be prevented and the charge will only be restricted to the capacitors and stored successfully. Next, we have our load, which is a CPU fan basically, and the supply or the storage that we have already stored in these supercapacitors will eventually be supplied through this switch to this CPU fan. And we have used this CPU fan for a very particular reason, because it draws a very little amount of current, which is very essential for our project, which can also be proved very helpful, because the elements that we have used in our circuit is a very kind of small element, and this project model will allow the CPU fan to rotate in a very significant speed. So that's a very positive thing for our whole project. So first of all, we are going to rotate this shaft of the DC generator for a particular period of 1 or 2 minutes. So now, if we turn the switch on, we can see the fan is rotating in a very good speed. And this was all the purpose of our project, to store the power from this generator to these capacitors and then supply it to a load. So the voltage that we are directly getting from this DC generator will be shown in this multimeter. So the maximum voltage that it can reach is approximately 12 volt, which is the rated voltage of this DC generator. The output that we can get from the IC or the voltage regulator is approximately 4.27 volts. This drop has been caused by the diode that we have used in this storage panel. So if we turn the switch on, the fan starts rotating and the voltage remains at 2.73 volt and it's still decreasing. So the fan is turning off and the voltage is decreasing here. The fan will eventually turn off now. Here the fan stops at 2.04 volt. Here is the Proteus simulation schematic of our project, where we have used a 12 volt DC source which is representing our permanent magnet DC generator. Here's the bridge rectifier, and that's the 7805 IC, and this diode is connecting the IC's output to our storage panel's input, which has been represented by a 5 farad capacitor, and it's our load fan. So when we are running the simulation, and if we close this switch, the storage panel is now storing power, and this voltage is increasing. So as you can see, when the voltage across this storage panel reaches 4.24 volts, it becomes saturated, and that is why we have disconnected the switch. Now if we turn this switch on, this charge will flow in this load. Here if you can see, the charge is flowing in the fan and the fan is running, and the voltage that is indicated over here is decreasing, and it will decrease until the capacitor fully discharges. So as you can see, the discharging rate of our storage panel is quite low, and that is why the objective of our project has been achieved. So we are terminating the run here. Now we move on to the extension part of our project. So for the extension part of this project, we were asked to come up with a voltage level indicator which can be used as an extension of the whole project. And for this voltage level indicator, we were asked to design without using any kind of IC or op-amp. The whole design included only LEDs and resistances, and if needed, Zener diodes or diodes. So the LED that we have used here is of 1.8 voltage rating, and that is why we have not been succeeded to detect the 1 voltage rating, because the LED that is available in our local market is not less than 1.8 volt. So that is why we have to start the voltage level indicating from 2 volts. So the first LED in our circuit is connected with an 100 ohm resistance, and it will detect the level of 2 volt. Then the second branch, we have a 1N4148 general purpose diode connecting with the LED and a 10 ohm resistance. this branch will eventually detect the voltage level of 3 volt. And the third branch, here we have used 1N4007 diode in 2 pieces, and the LED and then a 100 ohm resistance. This branch will detect the voltage level of 3.5 volt. As the voltage level indicator has been included with the entire project, the current drawn in this indicator will somehow reduce the voltage of the previous circuit that was kind of 4.23 volt, and it will reduce it to 4 volt. That is why we are not indicating the 4 volt level directly from here. So this is the hardware implementation of our extension part, which is a voltage level indicator. In the first branch, we have used this LED, which will detect 2 volt voltage level. This LED will first mildly light in 1.8 volt, and then it will be brighter for by time. The second branch, here we have used a second LED, which will detect the voltage level of 3 volt. This LED will start lighting in 2.4 volt, and it will eventually get brighter in 2.8 or 2.9 volt. In the third branch, we have used these 2 diodes, 1N4007, and this LED will detect the voltage level of 3.5 volt. This LED will start lighting from 2.9 volt and will be very bright since it reaches 3.5 voltage level. So now we are going to start this switch. So as you can see, the voltage level indicator and the fan is operating together in approximately 3.50 volt, and it's still decreasing as the charge is as the capacitor is discharging. So the third LED means the voltage level is quite 3.5 or above 3.3. So it will eventually be very mild, and ultimately it will stop lighting. And we have to see the thing that the second LED and the fan, if they both stop together, because the nominal voltage, or we can say the threshold voltage for this CPU fan is approximately will be 2.15 volt, and it will stop working in when it reaches 2.4 volt. So when the voltage is 2.4 volt, this LED will stop lighting, and the fan will also stop rotating. As you can see, the speed of our fan is now decreasing in a very quite good rate, and the voltage is also dropping in a very fast rate. So let's see where it stops. So now our fan stops, and the second LED has also stopped lighting together, and the voltage that we get here is approximately 2.06, where these two things stopped working together. The last LED that is indicating 2 volt voltage level will light for at least 40 minutes, and the discharging rate is quite low. Thank you everyone for watching our demonstration video. We are very grateful to our course teachers for their supervision and guidance. The detailed report with detailed data collection has been attached, and the link has been given in the following description of our video. Thank you.